All right, guys, happy Friday. We got here section 1, 2, segments, raise, and distance. Now, this is going to be our second section in our textbook. And although you're going to end up reading this section right here, I'm filming this video because still think it's worth having a teacher take you through it and point at some of the things that are in this section here. Now, I tried doing this on Wednesday with you guys, and things went a little bit too long. We left about 12, 15 minutes later than I was hoping to. So that's why I'm filming this video, because this is going to be your synchronous class. It's going to be kind of taking notes on this, and I'll be in the other room. You can ask me questions as well. And if this video drags on, then you'll just finish watching this for homework and taking your notes so that you have section 1, 2 done, and then you can do your homework. And your homework's actually not going to be until Tuesday on this section. You have your asynchronous class. You're going to do the problem set for section 1, 2. Okay, so let's go ahead and dive into it right now. Today we're going to continue classifying and differentiating new definitions. We will also get to our first rule. And in geometry, rules are called postulates, and that's going to be defined later on. So, of course, I know that I've been kind of hammering home about kind of the way that geometry is structured. It's different than you're probably usually structured in other classes. Of course, geometry, we want to prove facts. And the way we prove facts is through 3 methods. We use definitions, rules, and other facts to sort of defend why something is actually a fact. And we're going to study facts later, like the Pythagorean theorem, for instance. You've heard of that one. That one's a geometric fact. So anyways, we're still in this stage of just kind of classifying and differentiating definitions, getting definitions out there, and we're actually going to get some rules as well too, okay? Rules as well too. Are we going to get to facts quite yet? No, not yet, but facts will follow, right? Follow from having a bunch of definitions to have a bunch of different rules. We're going to get some facts, and it's not really going to be until section 1.4 that we finally get to a fact, but we'll get there, okay? We'll get there soon enough. All right, so we're looking at here a line right now, and we have a point here, B, point B in red, and so let's go ahead and start thinking about that one right there. We have here A, B, and C are all collinear points, right? Collinear points because we can draw a line through the 3. So remember that as a vocabulary word from section 1.1. How else might be categorized B's relationship with points A and C? Okay, points A and C. Well, B is collinear with A and C. B is collinear with A and C. So we know that already, right? That you're telling me it's something that I already knew, right? In section 1.1, Mr. Fortin. So B is collinear with A and C. But what's another thing that maybe we can say about B? What's significant about B in addition that we can run a line through A and C? Okay, B. B is between. Okay, so this is an example, and this will be important because we're going to get to a rule that will do with betweenness. Okay, between is what our first blank is here. And between actually isn't a definition. It's just something worth observing, that when you have a point between another point, that means that that point is collinear with 2 other points. And on either side of that point are the 2 other collinear points. That one point. Anyways, I said a lot of words. Maybe we should just read it here. B is between points A and C. And note that the word you just wrote, between, is not formally defined. It is technically an undefined term, although it's not really credited as being an undefined term. Anyways, it's not a defined geometric thing here because it's simply described. We're describing a point that's on a line AC, okay? That point that lies on the same line, collinear with A and C. But A and C are on opposite sides, okay? Opposite sides of B, okay? So we have this one line right here, and, right, one line. So we know they're all collinear, and A is on this side of B, C is on this side of B, so that means B is between A and C. All right, so now that we got between this, we can actually talk about directions that kind of, definitions that kind of have to do with these points here in front of us. Okay, so another thing to point out here, guys, what do we call this whole line right here, right? We've already done it down here. Yeah, this is line AC up here. Okay, so remember, a line, you need to mention 2 of the points and gets like these arrows here. That means that this is that undefined term that continues onward forever, right? On this sort of left-right dimension right here, okay? So beyond that, you guys should have heard of segments by now. Segments are part of a line, right? Are a subset of a line here. Anyways, segment AC denoted here, AC consists of blank, A and C, and all blank that are between A and C. Okay, so a segment AC, I think you already know what a segment AC looks like. Segment AC would be this here, right? Let me just move it down here. This is segment AC. I just moved it down here a little bit. Segment A and segment C, and we have ourselves segment AC right here. This is a segment. Okay, so this is defined. If we're actually draw a segment, maybe I'll redraw it down here because I think it's meant to be redrawn down here. This would be a segment AC because it consists of A and C. And A of C, what might be a good word for A and C right here? The points that are at the both sides of the actual line segment here. These are called endpoints, okay? So we'll call them endpoints over here. Endpoints are A and C and all points in between. So this here is the whole segment, and it consists of 2 endpoints and all the points in between that are between A and C. So this point's between A and C, this point's between A and C, this point's between A and C, all these points are between A and C here. All right, moving onward, we got ray AC. So I just want to get through these definitions real quick so we get to some rules and get to some practice and get to more definitions later. It's kind of a lot of stuff here at the beginning, but geometry gets interesting after we get through all of this stuff. So that's why I'm trying to get through it. Okie dokie. So another thing you need to be familiar with are rays. We got here ray AC. Ray AC consists of blank and all other blank P such that C is between A and P. Whoa. That's kind of confusing right here. Okay, so ray AC. So we're dealing with AC right here. I'm going to kind of move this one down here. So AC, okay, let me just draw AC again as a segment right now. So AC is a segment right here, but this is ray AC. Look here, I have one arrow at the right side of this, okay? And it's over C right here, okay? So ray AC consists of blank and all the other blank P, such that C is between A and P. Consists of points A and C and all other points P. Oh, this doesn't make sense. This is what I meant to put here. Let me actually draw out the ray for you here. Ray AC is actually this. Boom. Okay, this here is ray AC. So ray AC consists of segment. Okay, segment AC and all other points P such that C is between A and point P. Okay, so what they're just saying right here is that a ray basically here we have an A, and then it goes towards C, right? Goes towards C here, and then it contains all the points beyond that are on line AC, this direction. So here we could have a point P here, right? Make this P1, make this P2, make this P3. All these points are part of the ray. Here we have a ray shown for us here. Okay, so one thing that is worth pointing out right here too is that the end point of AC, of ray AC, is A. This is the point named first, okay? And this is kind of confusing here because let me give you another example that might be a little bit confusing for people to figure out. Let's have a array BZ, for instance, like this, okay? Array BZ, for instance. If I put Z right here as a point and I put B right here as a point, how would I draw that ray? How would I draw that ray? Well, BZ. Which one's the endpoint? Which one's the endpoint? This is the endpoint right here, okay? So B is the endpoint because look at that. There's no arrow on top of it, endpoint. So this ray is going to have to go towards Z. So here, this is going to be the ray. Starting at B, going to Z, and going on forever, right? Going on forever. This here would be ray BZ, ray BZ. So it's a little bit confusing because here B is on the left, but B is on the right down here. It's just a matter of what the orientation is here, okay? Another definition down for you here. Opposite rays are blank that share the same blank and travel opposite directions, okay? And opposite rays, right? This sort of gives you a little hint about, again, we need to classify this and then we'll differentiate it. So to be opposite rays, we're gonna have to talk about rays, of course. These would be classified as rays that share the same, what do you think? Share the same endpoint. Rays that share the same endpoint, but it's a little bit more specific than that. It's differentiated further than that, and they travel at opposite directions. Okay, so let's think about this here. We have a ray. Let me just draw one ray in right here. So I'll draw a ray S. Okay, what is here? SR, for instance. Let me draw SR. So I'm going to go this way. This would be SR. Look, S is the endpoint right here. And R, right, so the ray Of course, the ray is defined as the segment SR and all other points beyond R, where R is between P and S. So this would fit the definition of a ray. And in order to get an opposite ray of that, right, SR's opposite ray than that, it's they would share the same endpoints. And of course, right, you could draw in this ray. Is this an opposite ray, actually? Is that an opposite ray to ray SR? Ray SR? No, because it doesn't fit this part of the definition here. It doesn't travel in opposite directions here. It's traveling in just a direction. It just has an endpoint. So there are more, like infinitely many rays you can draw with S being an endpoint, but the one that is the opposite ray is this. Okay, it is collinear with that other ray, and it shares the same endpoint here. Okay, so this is ray ST in this situation here. So these are examples of opposite rays. Okay, opposite rays are going to be collinear with one another. And that's what we have for opposite rays. Okay, so be on the lookout for that one when you get into your homework as well tonight here. Okay, so quick status check here. We got kind of our definitions down. Starting up here, segment, right? 2 endpoints, all points in between. Ray is a segment, and then all points on one side of that other point that's not the endpoint of the ray. Kind of confusing how array is defined, but this is the best way your book can define it for you in words, and then I drew it out for you here. Remember, the first letter mentioned in a ray is what? The endpoint of the ray, and the other point is just another point on the ray. It just shows you which direction that the actual ray gets drawn. Finally, opposite rays, collinear. Share the same endpoints, okay? But they're going in opposite directions here, okay? So quick question here. Let's ask you this one here, actually, about opposite rays. Let's do Z here. Let's do X here. I got a question. Is ZX an opposite ray of XZ? Are those opposite rays? No, they're not, because they don't share the same endpoint here, okay? So here, this red ray and this purple ray, not opposite rays. Okay, because they don't share the same endpoint. And that's just a quick one to clarify with you very quickly. Okie dokie, keeping on moving down here. Keeping on moving down. So the next thing that kind of your section goes into as you're doing it is talking about length of segments here, okay? So this is kind of nice because finally you're getting to a part in geometry where we're going to talk about numbers, right? After all, geometry is a math class, so it deals with numbers eventually. What's gotten defined so far? Let's think about it. We had the undefined terms on Wednesday, and we defined a few things beyond that: collinear lines, space, collinear points, non-collinear points, and then non-coplanar points, etc. So pretty much things that have gotten defined for you right now have been shapes. The next thing that gets defined for you is actually going to make space for a number. And that's nice because we want to get numbers into problems and be able to practice this kind of stuff. After all, it's all about practicing and thinking critically and getting better at this stuff here. So segments can be measured on number lines, right? So any segment, we can actually make a number line out of it. And I'll get to that a little bit later, right? So segment JL, we can drop a long number line if we wanted to here. So we use a number line to measure the length of a segment here, okay? And this is a definition right here. We define the length of a segment as the distance between the two endpoints of a segment here. Length of a segment is the distance between the two endpoints of a segment. We haven't really defined distance yet, but I think you get the idea, right? How far do we have to go from J to L, for instance, on this number line is going to be the length of that segment JL, okay? Another thing, a very, very important thing to point out here, guys, so try to pay attention. Just really, really hone on this one here. Very, very important is that these are two different things right here, okay? We refer to the length of segments, okay? This is pronounced segments JL, right? Remember we have this little bar up top? That's what we had up here, little bar up top. This just stands for segments. We refer to the length of segment JL as just JL with no segment on top of it. But what you say when there's no segment bar on top of it, that stands for distance or length. This stands for length JL, okay? We don't see the 2 points in front of one. We can call it length JL, or you can actually call it distance JL because it represents the distance between the 2 points, J and L. And this is the thing to be on the lookout for in problems here. If we just write the two letters of the points next to one another, right, nothing on top of the letters here. So notice here, right, JL is a distance. The JL with a segment bar on top of it is a shape. Okay, it's a shape here. So if we just write the two letters of points, just like this one right here, next to one another, that means the distance between those 2 points, the endpoints of segment. And distance is a numerical value. I'll get to all that later. If we wanted to find the length of segment AB, okay, I should have had this one up here, the length of segment AB, and I guess read out loud, this would have been segment AB anyways, even without that up there. Anyways, I digress. If we wanted to find the length of segment AB, we would just write AB. Okay, AB, because this is a distance / number. It's the length of segment AB, okay, with nothing on top. If we wanted to find the length of segment XY, we would just write XY, right? That's all we'd have to write here. So note here, again, JL with the little segment bar on top of it, it means segment JL, which is a shape. JL with no segment bar on top of it, that means distance JL, which is a number. We can figure that out right here, right? The distance of JL, right? JL would equal what? What's our distance here? We can count them up, right? We can do some math here as well. We can count them up. 1, 2, 3, 4, 5. JL would equal 5. Okay, JL would equal 5. What we're not allowed to do is this. We can't actually say JL equals 5. Why can't we do that? Okay, why can't we do that? Well, segments got nothing to do with distance, right? Segments aren't defined for distance. What did we define for distance? We defined the length of the segment here, okay? So this would read as length JL, length of segment JL is equal to 5 units. This here does not matter at all, right? Does not matter at all. That being said, let's find the distances here. Take a second, try to get these ones done. We'll fill in the answers. Give this one a shot. Ready, set, go. What is length JK? What is length ML? And so on and so forth. 45 seconds, and then we'll go over the answers. Ready, set, go. This one's here. So these should have been pretty straightforward here. Look, JK, that's just 3 units. I could count them. I could also subtract, right? If we go to the right side and we subtract, we would get our answer. So 0 minus -3 is +3. Remember, distance is always positive. ML, that's 2 units, right? 4 minus 2 is actually 2. So I usually go to the right side because the right side's a bigger number on a number line, right? We get more positive this direction. We get more negative this direction, or at least that's how most people set up number lines here. I'll get all that later a little bit here. So using this logic here, if this is the positive side and that's the negative side here, then obviously this y coordinate, these are actually all called coordinates down below, even in geometry, this y coordinate here would be larger than this x coordinate here. So we could take the larger one, subtract the smaller one, and that's going to tell us this distance here, So this distance here is going to be whatever this is, right? So this is 5 and that's 3, then this would be 2, right? 5 minus 3 equals 2. But here, this is y, that's x, so it's y minus x here, okay? So note here that this didn't say positive or negative here, although we can see the numbers increasing. So one thing you could have done, right? One thing you could have done to be safe here, when you have variables, to get a distance is I could actually do the absolute value here, okay? Taking the absolute value of the difference between two coordinates gives you the distance between those two coordinates, between those 2 points here. Okay, so I'll write that down. We'll actually get to that later in a particular rule that will come up here. So the absolute value Okay, so the absolute value of the difference of two coordinates gives the distance between the 2 points here. Okay, so I just put this down here in the formula just to be a little bit safe here. So we can actually think back here and like these other ones up top just to kind of double check here. 2 minus 0 is 2, but what if we had actually done this coordinate here? So given two random coordinates, like so we were given the coordinate for k and coordinate for L, what could we do to make sure we got the right distance? Well, I could do this coordinate here, right, 0, and then I could subtract 2 from it because that's the coordinate of L, but that would be negative 2. What's the distance between the two? Oh, it's positive 2. So as long as I take the absolute value here, right, of the difference between two coordinates, I get the distance between those 2 points here. That'll definitely come up on homework. What's the problem with this one, guys? This one here, segment KL equals, well, segment KL doesn't equal anything here, okay? Because this is not a length. That is just the segment. So we're not going to get an answer right here, okay? You should never see segment KL next to an equal sign. Why? Because it is a shape, not a distance. Okay, you should have said KL equals instead, and KL would equal 2. All right, moving onward. Okay, so those were some initial definitions. Again, you'll reread them for homework in the next section. Part 2 of this is going to be some postulates, some rules, and then we'll get some practice on that, like actually practice problems. And then after that, in part 3, you get a few more definitions. Again, we're just kind of dumping stuff, introducing stuff out so that we can actually get to fun fact-proving stuff a little bit later. Okay, part 2 is postulates here. We get a pretty big definition right here, and that's actually what a postulate is. So remember, in deductive reasoning, right? Deductive reasoning, the way you can make a deductive argument and prove a fact, right? Prove a fact here in these sciences that we're doing, in maths that we're doing that are deductive. To prove a fact will require having 3 things: definitions, rules, and other facts are the things to kind of get this there. So here, what a postulate is a very basic assumption in geometry that is accepted as a rule without being proven, okay, without being proven. So if you had to pick one word in this definition of what a postulate is, in terms of what I've been trying to focus you guys on, is that a postulate is a rule, okay? So if the goal is in our deductive reasoning to use facts, rules, and definitions to prove new facts, to justify new facts here, postulates are the rules, right, are the rules behind it, okay? So postulates can oftentimes get mistaken for facts. So you might want to know what the difference is between a fact and a rule here. Okay, so the difference is that a postulate is a very basic assumption. Okay, very basic assumption. So it's something that is so obvious, almost like common sense, right? Something that's very obvious, almost like common sense, that we just accept, that everybody knows that's got to be true. It's got to be true. But it can't be proven, okay? Proven, okay? Because facts are proven. We're going to get to proofs later, and postulates are not. Facts are proven, that says facts here are proven, and postulates are not, okay? So let's get into the ruler postulate, which is our first postulate of the textbook, and we can actually take a look at it here. The points on a line can be paired with the real numbers in such a way that any 2 desired points can have coordinates 0 and 1. The distance between any 2 points equals the absolute value of the difference of their coordinates, okay? So I've actually kind of already done this one here as a common sense thing in the last one, right? This is common sense, okay? We'll get to this later. I sort of cleans it up for you here as the takeaways, right? In order to find the distance between 2 points, take the absolute value, subtract their 2 coordinates, you're good to go. You're golden. You got the distance between those 2 points. Second thing here for the ruler postulate is that any 2 desired points can have the coordinates 0 and 1. Huh, that's interesting. What does that mean? Well, what that means is something like this. If we have 2 points, and let's go ahead and draw 2 points in here. We have A, B. Okay, what's stopping us here? A, B. What's stopping us here from saying that if I drew in a line and on a number line, points A, I'm going to put A up here and put B right here. Okay, let me actually get rid of this. What's stopping us here from saying that this has a coordinate of 0 and this has a coordinate of 1? Nothing, right? Nothing's stopping us of this. So remember, measurements like the meter, the foot, the centimeter, measurements are a human construction here. That's just simply, right, kind of arbitrarily, these 2 points could be 1 unit away. And then, right, if we wanted to repeat this segment over here and we had the point C over here, that's also 1 unit away. This would be 2, okay? We'd have another point here, right, that this is 2.3 or something like that here. Okay, so what this is saying is that you can set up a ruler however you want. to kind of measure out the distance between 2 points, or what you're going to say is the distance, and then use that going forward. Okay, so takeaways from this: we can scale any distance however we want on our ruler, describing the distance between 2 points. Each point gets assigned a coordinate. Okay, what that tells us is that, hey, if we want to make this 1 unit long, cool. Then anything that is this size right here would be 1 unit long, for instance, in distance. Okay, this will be important later when we're trying to prove things, and maybe we want to copy a particular segment, right? Copy a particular segment. So this is something that doesn't really come up that much. Ruler postulate doesn't come up much, but we'll use that to add stuff to diagrams. We'll do that later. Okay. What's more important, eminently important for your homework right here, is that this formula, you got this down as a formula. So make sure this formula is in your notes. Okay, the distance between 2 points, follow this formula. And right, this is representing x1 and x2 are the coordinates, right? Coordinates of those points. Okay, so if we had a point, right, a point z and a point y, and say this is a coordinate, say this is 3 or something like that, and this is this is 1 unit, right? We're just laying out our ruler, 4, 5, we would eventually get to y, and then we just have to subtract the 2, take the absolute value, and you're good to go to get the distance. If we didn't know the coordinates, right, and we just had the coordinates be x1 and y2, right? If this is x1 right here, and this is x2, sorry, I should have said x2 earlier here, you simply just have to take this one, subtract that one, and then remember, distance is always positive, so take the absolute value. That would give you the distance here, okay? A little more practice, guys. Get these ones real quick. 30 seconds. Take it away. I'll be doing them too, and you can check your answers in a second. What's distance kj? What's length km? What's the length of segment pm? What's distance qp? So notice that you can say this is the length of the segment formed by points k and m, or you can just say it's the distance km. Ready, set, go. And there we go. We got our answers, right? We got our answers here. Notice here, right? If we just change this to x minus 4, right? X minus 4, that might be a negative number. It might be a positive number. But if we took the absolute value of that and took the absolute value of 4 minus x, they would actually equal the same thing, right? One of those would have to be as much below negative, right? 4 minus x would have to much below negative as x minus 4, for instance, would be above negative here. So anyways, this is kind of the way you do it. And I hope you got the same answers as I did, or you got kind of, this would have been acceptable too, right? So one of these has got to be negative, and it would be just as negative as the other one is positive. Okay, so either any of these examples would have been sufficient here. Okay, so here, this one became negative, so we made it positive, right? If I did 0 minus 3, sorry, if I did 0 minus negative 3, I would have gotten positive 3 anyways. And the absolute value of that would have matched the 3 here. Here, if I had done 4 minus 0 the other way around, absolute value of 4 would equal the absolute value of negative 4. Good to go. And we can apply this to this stuff here. It gets trickier with the variables here as we go through. Okie dokie, keeping on moving now. Moving on down here. The following rule comes up a lot when we're proving facts this year. You guys are going to take notes now on the segment addition postulate. This is going to come up on a lot of proofs. When we do proofs to actually prove facts, it'll involve the segment addition postulate. So you got to make sure that you know what this is talking about here. Okay. Nice. Okay, so we've talked about between already. I see the word between in the segment addition postulate, and that's nice because we talked about that, and we'll talk about this in a second. But it looks like we're also getting some math here, which is kind of nice. So we're getting an addition symbol here. This is called segment addition postulate, or if you want to abbreviate it, you can abbreviate it a whole bunch of ways. You can abbreviate this segment addition postulate. Okay, and that's fine too. And let's talk about this, what this is exactly. Okay, here we go, we postulate here. If B is between A and C, then length of AB plus length of BC would equal length of AC, okay? And that's going to make total sense, I think, in a second. What we might need to do is actually draw this out in a diagram here. Okay, let's check this out here. If B is between A and C, so let's maybe draw out what that might look like. Okay, let's get A and C first, because then B would have to be between A and C. So B would be maybe right here, let's say. Sure, that's between A and C. And let's draw in that line segment. Okay, make these endpoints pretty big here, and then this point is just on segment AC. So if B is between, so B would be collinear with A and C, and B between A and C, be on segment AC, right? If it's between A and C, okay? So if we know this here, then what we would know is that, right, AB, which is this, right? This is distance AB right here, okay? This is distance AB, right? We would know that distance AB plus distance BC, this distance right here, okay, it would have to equal AC, okay? And AC is right here, okay? AC is right here, okay? So what this is just telling us is that if we see a point between two other points right here, we can add the lengths of these smaller segments, okay, the smaller segments to equal the length of the larger segment, okay? Or another way that I refer to this postulate here is a part of this segment, a part of AC plus the other part of AC, because B is between A and C and B is an endpoint of both of these smaller segments here. A part plus part equals the whole segment, okay, the whole segment here. So you'll definitely hear me say that out loud quite a bit here, okay? So if B is between A and C, then the part that goes from the endpoint to that point B to plus the other part from that point B to the other endpoint here is going to equal the length of the whole segment, the length of the whole segment AC. Whole segment AC, okay? So this here is going to be useful for adding numbers together, which we'll have later, right? If AB were 3, BC were 5, then sure, we can make the conclusion that AC has got to be 8. This is a postulate because this is very, very obvious. There's no way, we have no methods yet to prove that this is actually going to be true, right, 100% of the time, but it's super obvious here, right? If we had a specifically large segment right here, and let's say that this is 10 units in length, and this is 13 units in length, then the whole thing, right, would be 23, right? Perfectly logical. I think we can accept this without proof, without just like this has got to be true, right? Got to be true. It's so obvious. We can look at it. We'll accept it right here. Okay. Note here down here. So I wanted to point this out to you because postulates, okay, postulates are oftentimes, almost always, it wasn't in the very first one, not in the first one, the ruler postulate, but almost always are written as if-then statements, okay? If-then statements. What are those called again? If-then statements? What's the other word we have for if-then statements? That's right, a conditional statement. Okay, conditional statements here, okay? So because of that, when we study these postulates this year, I might kind of summarize for you what a postulate's doing by you doing these symbols right here, okay? Let me get into this real quick because this is actually something I usually teach at the beginning of the year, but because of distance learning, right, I just don't want to bother with it, but it's still helpful when we get into geometry, is that an arrow, a single-headed arrow in math actually stands for if-then. Right? If you keep studying math, you're going to see this a lot. A whole bunch of if-then statements. If you study computer science, you'll see this a lot too. If we do this, if we program this, then this is going to be the result. Or if we have these particular shapes and they look like this, then we're going to be able to conclude this, right? It's how it works in geometry here, okay? So this is a conditional statement. This postulate, right? This is, right? This postulates are almost always conditional statements. Note that this postulate is a conditional statement. In math, any conditional statement can be symbolized through a right-facing arrow. So here, right, this arrow right here, right, it stands for, it's a conditional statement. It means this arrow here, this rightward-facing arrow here, stands for if, then. Okay, if, then. So taking what I just talked about right above us here, okay, right above us here, the thing that is on the left side of the arrow, that's where your if is here, okay? If in a particular situation, it's given to us that we have a segment, right? So we have like segment AC, like this, AC, and we have a point in between here. We have a point B in between here. If we notice something like this, then, okay, so if we have this, then this arrow, right, gets us from if to then, to a conclusion we're allowed to make. And we're allowed to make this conclusion by postulate, by rule, by this assumption that this has to be true, that AB plus BC would have to equal AC. Okay, AC. So this seems very, very obvious, but it'll definitely be used in proofs of facts once we get to facts in section 1.4. Okay, spotting this here, guys, because you're eventually just gonna be able to see this. Here's something I can do with this. I have this diagram. I know that there's something that I can do, and the segment addition postulate is the reason why. Okay, so when I symbolize postulates and theorems like this, I put the reason inside here. Again, left side of the arrow, what does that mean? This is the if part. Okay, this is the if part. So if we have this as a diagram, then, and I usually don't write if then here, but this is how I got it set up. If we have this, what are some conclusions we can make? We can think of, I can actually think of maybe like 3 conclusions we can make right now. More than that, I think maybe 4 conclusions. Let's see. Maybe not 4. I don't know. Let's check it out here. Well, how about this? Can I make this as a conclusion? DO plus OW equals what? DO plus OW equals what? Well, O is shared here, so O is between D and W, so that means that equals DW, okay? Here, again, we have part plus part equals whole, okay? What's another one? So let's do the whole thing then, right? Let's do the whole thing then. What about DW plus WN? What does that equal? Okay, what does that equal? Well, DN, okay, equals DN here. So W is between D and N, so DW plus WN equals DN. I think you guys get the idea. I hope you get the idea here. I can do DO plus ON also equals DN. Okay, what else can I do? I can think of one more I can do. What haven't I done yet here? Well, I've talked about WN a couple times, but I haven't talked about ON yet, have I? Well, I have talked about ON here. What do we got? I haven't talked about ON being the whole part at least. I can do this part, right? OW plus WN equals ON. Okay, so I'm going to do that as another thing that I can conclude. Reasons for all of these that I'm doing, right? Well, the reason's right there, segment addition postulate, okay? So I can conclude any of these 4 things right here, okay? In this particular diagram, right? If we have this as a diagram, then we can conclude these things here. One more, how about the bottom one down here? We got one more here. Give me just one thing here. By the way, guys, do you remember what is the statement or what is the thing that appears after an if statement, okay? So let's look back up here. Let's actually look back up here. Do you guys remember this? Oh, man, it's getting messy up here. So it's getting messy up here. So do you guys remember this? After the if, okay, after the if, there's a statement, and this is a yes or no statement here. If B is between A and C, do you remember what B is between A and C is? The part that comes after the if. There's a vocabulary word that comes with that. What part of the if, that conditional statement is that? There's a part after the if, and then the part after the then. Okay, part after the if is called the what? Called the hypothesis. Part after the then, what's that called? Called the conclusion, okay? So given a situation like this where B is between A and C, we can conclude, right? AB plus BC equals AC, okay? So it looks kind of crazy at the beginning, but it's actually pretty easy as we can kind of see here. Okay, so here we have our hypothesis, which is our if this is our diagram, and then we can get to conclusion. What can we conclude? I don't know. What can we conclude right here? Well, I can say a few things. How about, well, here we have a part right here. We have another part right here. And then we have a whole, right? Part plus part equals whole. And I'm still having trouble writing with my stylus right here, okay? So I can conclude BA plus AN equals BN. That's one thing I can conclude. Part plus part equals whole. Okay, what about down here? It looks like I got another one. Okay, I got another point in between. So A is between B and N. B looks like it's between L and E. So what can I conclude? I can conclude LB plus BE equals LE. And we're good to go. Okay, so just reminders on this particular postulate. It is part plus part equals whole. And we're going to get a similar one for angles in the next lesson in section 1.3. Okie dokie, we got some algebra to practice now, guys. This is directly in the section here, so you can see how to do it, but I think you guys can figure this one out. Let's check it out here. It looks like I got my x moved over a little bit, so I got to adjust that. I want my x right here. So guys, I want you in this diagram right here. How can you solve for x? And then how can you solve for length BC? Notice here, we don't have this, we're not solving for segment BC, we're solving for the length of segment BC, or distance BC, the distance between points BC, okay? So take 2 minutes, see if you can figure this out, and then watch what I do afterwards, okay? Ready, set, go. Try out this example algebra. Ready, set. Okay, so we have x here, so this is variables, right? That's why I call it an algebra problem that's here in Geo for us. Using the segmentation postulate, I'm gonna talk quietly in case you're still working. Using segmentation postulate, we know that AB plus BC would have to equal AC, okay? So in order to solve for x right here, right, we might wanna take what AB equals, and AB equals x, okay, equals x. And BC equals x plus 6. And AC, so AC would equal x plus 6, but AC also equals 12. It's given to us that the length of the whole is 12. So part plus part equals whole. And what's nice here is we only have one variable, so we just got to solve a one variable equation. You should definitely know how to do this from Algebra 1. If not, come check in with me. I can find you extra practice. X plus 6, well, we can drop the parentheses there, combine like terms. We have x plus x, and that's just 2x. And then we have a plus 6 remaining, and that equals 12. We're going to subtract 6 from both sides, and we're going to get 2x equaling to 6. Divide both sides by 2, and we're going to get for x, okay, 6 divided by 2 equals 3. And that's what x equals, okay? So x equals 3. Is that the whole answer, right? So this is a tricky thing in geometry. A lot of people make this mistake. They stop answering the question once they figure out what x equals. Okay, were we just asked what x equals? No, we're also asked what BC, distance BC is. And BC equals x plus 6, okay? So what we're gonna do is we're gonna take this 3 here, because that's what x equals. Okay, x equals 3, and let's drop it in for x down here. Okay, so we're gonna get 3 plus 6, and BC equals 9. And I'm hoping you got the same thing that I got in both of them. This example's in the book too. Please check it out if you get a chance. Okie dokie, guys, we're almost there, guys. These first few sections are just like, man, just dumping stuff out here, getting it out here. And literally, like the first chapter is just such the worst chapter, to be honest. Like, I like chapters that sort of build on it once you actually get into the swing of things here. So anyways, we just got 3 definitions to go, and then I'm going to do another example, and then, hey, we'll be done with those. We'll be done with this lesson right here. Okay, we're almost there. Just 3 more definitions to go. You can do it. I believe in you. So let's get it here. We got 3 definitions, 1, 2, and 3. And then, hey, little practice problem. No, maybe I'll talk about your homework and you'll have a good weekend. Okay, so congruent segments is the next thing here. Congruence, okay? Congruent segments. Man, whole bunch of vocabulary here in geometry. Congruent segments are what that have what? Well, if we're talking about segments right here, right? We're talking about segments right here. Congruent segments, well, they got to be 2 segments, okay? Or just segments. Multiple segments at least, because it says congruent segments. And what do you think congruent segments have? Congruent segments. Well, let's look at the symbol for congruency. What do we see here? The symbol for congruent segments is congruent to. Well, I see an equal sign. Interesting. I see an equal sign with this little squiggle on top. This stands for is congruent to. So if it's equals, right, I'm guessing that congruent segments are going to be this. Okay? Segments are maybe going to be this. So we got here, maybe let's make this segment AB. And we got this as segment CD. And I'm guessing these would be congruent if they were the same length. Okay, so if this were, say, a length of 6 units, and this were a length of 6 units, then CD, segment CD, would be congruent to segment AB. Okay, segment AB. Okay, so congruent segments would be classified as segments. How are they differentiated? Just by any 2 segments. How are they differentiated? There are 2 segments that are exactly the same. They have the same length. Okay, the same length. And we've completed that definition right here. Okay, congruent segments are segments that have the same length. They're exactly the same. They're just located in different places right here. And this symbol here right? This symbol right here stands for is congruent to. Is congruent to. And this is similar to equals, right? Equals, what this is, you call this the equals sign, you call this the congruency sign, but what equals really translates to is equal to. Is equal to. So one thing, we're going to read geometry the same way we read algebra. We read it from left to right. So if we had like 5x is equal to 10 is similar to how we can write segment CD is congruent to segment AB. Okay, so just wanted to point that out. All right, looking downward here. Oh man, I'm dropping another big guy into you here. Here, notice here, we actually don't have a single-headed arrow on the right side here. We have a double-headed arrow. Okay, we have a double-headed arrow. So here we have segment DE is congruent to FG, and I have a double-headed arrow here. So this is, I'm going to reword this definition because this is actually kind of a helpful thing to kind of take notes on and kind of make your notes a bit shorter if you're taking down definitions in the future here. So here, notice that when I told you before, what did the single-headed arrow mean here? What did that mean? Okay, if you have a single-headed arrow like this, it means an if-then statement. Okay, if this is true, then this has got to be true here. This double-headed arrow means something a little bit different here. Well, this means that if DE is congruent to FG, then, right, then we can conclude what? They have the same length. So we can conclude that DE equals FG. Okay, we can conclude that by definition of congruent segments. Congruent segments are segments that have the same length. So if they're given to us as congruent, we know that they have the same length. We know that DE would have to equal FG. There are two-headed arrows here, right? Two-headed arrows here because what the definition is telling us is not only is the arrow going this way going to be true, this would also be true. If we knew that length DE equals length FG, that would be enough to prove that the two segments are congruent to one another. DE is congruent to FG, segment FG here, okay? So for definitions, okay, definitions gets this, and let me erase this right here. Definitions get this double-headed arrow in the way that I'm going to abbreviate it for you guys here, okay? Because if we knew that DE were congruent to FG, then we can make the conclusion that DE's distance to E would have to be the same as FG. By definition, that's what congruent segments are. But also, it's double-headed arrow because we could go this way too, right? We could go this way too. If we knew we had a couple segments and their distances were the same, that would be enough to prove that the segments were congruent to one another, okay? So something that is said out here, right? This double-headed arrow, okay? Double-headed arrow means that one thing, knowing one thing is good enough to establish the next thing and vice versa here, okay? And what the arrow literally translates to is something called if and only if, okay? And if I put this into words there, right? If, I'm not going to put if right now, okay? So I'm going to erase this real quick, okay? The way we'd actually say this out in words is segment DE is congruent to segment FG if and only if DE equals FG. Distance GE is equal to distance FG here. Okay, so segment DE is congruent to segment FG if and only if. That's the only way that that segment's going to be congruent is if and only if the distances are the same, okay? And the if and only if in between is the thing that tells us that it's going to be both ways, can go both ways. I'm not sure if that makes sense, so maybe we need to keep talking about it and seeing more examples here. Okay, 2 more definitions to go. Guys, I meant to film this video to make this a bit shorter than the one that I filmed over the summer, but still I'm going kind of long. So hopefully you're with me. Hopefully you're taking notes. If you just kick back, and I know you have a lot of work to do, but you're going to be fine, right? If you try to kick back and enjoy this and get your notes in and then do your practice, you'll be fine this course here. Okay, anyways, midpoint of a segment. Midpoint of a segment is well, I think I see point right here. So midpoint of a segment is not a segment. Midpoint of a segment would be a point that divides a segment into what? Okay, well, you probably know what a midpoint is here. Okay, so let's get a segment AB again. Okay, what do you think the midpoint? About where would the midpoint? Tell me when to stop when I get to the midpoint of AB. Stop here, right here. Okay, so I'm going to mark this point M. Oftentimes in the book, you will see M be the midpoint, and because M is the first letter of midpoint here, okay? So it's going to be the midpoint of segment AB. It's the point that divides the segment into what? It's the midpoint here if, okay, this here, right? Say that this is like 3 units, and this is 3 units. Right? That would be the midpoint because it would be halfway in between, okay? Midpoint of a segment is a point that divides the segment into 2 congruent segments, okay? 2 congruent segments. Another thing that I wanted to point out about congruency that I'm noticing I didn't actually point out here is that congruent segments actually get a symbol, okay? Actually get a symbol. So CD, because it's 6 units, is congruent to AB. If you have this little tick mark on here, it's going to indicate that that segment, it's usually in red, this segment is congruent to that segment right here. Okay, so let me re-show this down below because I do this here. So M is the midpoint of segment AB if AM, if and only if AM is congruent to MB. Then that would be enough to prove that M is the midpoint of this. It would also be enough to establish that MP and then M would have to be the midpoint of that and whatnot, okay? So we have that there, okay? So remember, right, if I had a diagram, for instance, and I wanted to show that other segments were congruent, okay, I could do 2 tick marks, okay? So the amount of tick marks you get here correspond to whatever's congruent to in another diagram. Anyways, that'll come up a little bit later. Okay, double arrow means if and only if. So reminders, let's maybe symbolize what this definition is here because, again, you'll use these in establishing facts later on once we actually get to proofs and whatnot. So anyways, P is the midpoint of segment AB. What is the P as midpoint? So we can go directly from P being the midpoint of AB to saying that 2 segments are congruent to one another. So how are we going to figure this out? Looking at this here. P is the midpoint of AB. What are the 2 segments that are congruent to one another? Well, AP and PB. Those are the 2 congruent segments here, okay? So again, this is an if and only if statement because if I wanted to say this out loud, right, segment AP is congruent to segment PB if and only if P is the midpoint of AB, of segment AB. And I probably should also say that P is between A and B because it's not like a V-shaped. Anyways, I'm kind of getting a little bit ahead of myself here, okay? So if we knew that we had P being the midpoint of segment AB, it'd be enough to prove this. If we knew that we had segment AP congruent to segment PB, and we knew that P was between A and B, that'd be enough to establish that P has got to be that midpoint there. Okay, final definition. I know you're like, guys, you're just like, Mr. Fortin, is every section going to be like this? A lot of sections are going to be kind of like this, because that's just how this works. But it's really painful at the very beginning. There's so many definitions, and you haven't learned how to do anything yet. So that's what I'm trying to get you to here. Okay, bisector of a segment. Okay, so let's get to this here. Bisector of a segment. Oh God, man, bisector of a segment. So let's take a look at this diagram here to help us think about what a bisector of a segment in particular is here. So in this diagram here, how many segments are really shown? Well, we got segment PB, we got segment PA, we got segment QP. The only segment that appears to be getting bisected potentially is segment AB. Okay, so segment AB is bisected by, what do we think bisects segment AB? Well, bisects, what does bi mean again? Bi means 2. Okay, bi means 2. So 2 identical. So P looks like at point P is probably the midpoint of segment AB, right? Midpoint of segment AB. And that's already indicated here. I should have had that be a fill in the blank, but I don't. But anyways, we have segment AB, and the bisector of segment AB isn't going to be the midpoint, right? Because the midpoint, we know that there's going to be 2 congruent segments here. So maybe we actually put that down here. I'm assuming that P is going to be the midpoint. So let me do that. I'm going to tick mark this here and tick mark this here to indicate that PB is congruent to PA. If that's the case, the things that bisect this particular line segment are, well, a plane, okay, plane X looks like it bisects AB, right? It cuts AB in half, right? It goes through its midpoint. Segments, like the segment QP, that also looks like it's indicating where the halfway point is on segment AB. So we have a segment can do that too. And what else? What else goes through here? A line, sure, a line. What else are we missing here? A line. What's the other thing here? Well, also a ray, for instance. That may have been tough to see. This ray here. Sure, that ray bisects that particular line segment. So that can be it too. So a plane, segment, line, or ray intersects the segment at its midpoint. That plane, segment, line, or ray is referred to as the bisector, not the bisector, a bisector of the segment. So as you can see, there are several things, several geometric features, planes, right? A wall, meaning another wall halfway in between, like two rooms are identical, and a wall meaning that would bisect the segment that would be those two rooms as walls, right? So that could be a plane, it could be a line, it could be a ray, it could be other stuff here, okay? Anyways, let's see what this helps us establish this here. So this is definition of bisector of segments, of segment bisectors. This kind of goes by a few words, definition here. So if we knew that plane X bisects AB at P, what could we conclude, right? What can we conclude? Well, we can conclude that P is the midpoint of AB, okay? If we knew that plane X bisects AB at P, then that means plane X is going through the midpoint of segment AB, thus bisecting it. Thus, we can conclude, if it goes through the midpoint, that AP, not AB, AP is congruent to PB, and that is that. And guys, you've made it. We just got a little bit of practice here. I got a closing problem, and then we're going to homework, and man, you made it. And wow, this is a lot longer than I was hoping, because I've already filmed a video for this lesson. I was hoping this would be shorter, but I think we got to go through all of it. Anyways, closing problem down here. This will actually be very similar to one of the hardest problems on your homework. So if you can solve it, hey, you're in great shape. The hard part really was just watching this video, taking notes, and feeling like you're in a position to do these problems. Give it a shot. So let's just try to get it this shot now, okay? So here, look, this says exercises 31 to 38. It's pretty late on the homework here, so that's why I say it's one of the harder ones. So see if you can do this along with me here. Using the information below, find the value of Z, then find distance GE and length EH, the length of segment EH, and state whether E is the midpoint of GH. Lots going on here, so I think we maybe need to label. Looks like they gave us more algebra too for what these segments, an algebraic expression for what these segments could be represented as here. Okay, so I'm just gonna start labeling this up. I'm not gonna think too much of the problem, because we're given here that this is Z plus 2 is what GE is. So the book usually does this in red, so I'll do this in red here. This is Z plus 2 is GE. GH is 20, okay? Ooh, 20. So I'm going to do this here, 20, okay? And EH is 2Z minus 6, okay? So it looks like DF is kind of a distraction to a certain amount of time here, because we have point E, okay? Point E is between, right? Point E here, point E is between G and H. So that means we can use what? We can use the segment addition postulate to solve this one algebraically. You'll use segment addition postulate in fact-finding missions when you're writing your proofs in a few sections, but now you're just using it for some algebra right here. Okay, so we need to send up an algebraic expression here. Looks like we need to solve for Z first, okay? So it says find the value for Z. That's what we're going to do first, and then we're going to do this second, and then finally we're going to do this third. There are three things we have to do, so let's find Z now. To find Z, we just need to set up an equation with Z. Very good. So what I know about segment addition postulate is that I'm going to do part, so GE, plus the other part, EH, equals the whole. And so the whole is length of GH right here. Length of GE plus length of segment EH equals the length of GH. Or distance GE plus distance EH equals distance GH. Man, if you're just soaking this all in, I think it's fine. I think it'll be fine, okay? So what we got here, GE, that we're given some algebra for that, so let's go ahead and substitute that in. Z plus 2. EH, we're given some algebra for that one too, so let's substitute that one in. 2Z minus 6. And GH is going to be 20, right? We're given 20. Or it's the sum of this too, right? They're equal to each other. This part plus part equals whole, and now we can just solve it here. Let's just do some algebra, and mathematically, we will get this solved here. Bet you thought Mr. Fortin couldn't have been any cooler, and then he had to say mathematically. Okie dokie, z plus 2z, combined like terms, that is 3z. Oops, I wrote a 2. I meant 3. 2 plus negative 6. Well, 2 minus 6 is going to be negative 4. Combined like terms, that equals 20. Okay, we got to add 4 to both sides so we can isolate the z term, and we get 24 over here. Now we can just divide both sides by 3, and z is going to equal 8. That's number 1. Okay, we knocked out number 1 up top here. Z equals 8. Hopefully that's what you got. If not, go back, watch the video again, retry it, ask questions here, okay? Step 2, find G and EH. So you always go back in geometry, always go back to make sure you answered the whole problem. That's very, very important here, okay? So this was number 1. Let's do number 2 over here. Stay organized. Hopefully you can follow what I'm doing here. And we got to get GE. Well, GE is Z plus 2. And Z we got is 8, so that means it's got to equal 10. GE equals 10. And let's make this nice and quick and just do EH in our heads. Z is 8. Oh, let's not do Z in our heads. We'll do 2 times by Z, which is 8, minus 6, okay? Because notice here, EH equal 2Z minus 6. So EH is going to equal 2 times 8 is 16, minus 6 is 10. And, ooh, okay, interesting. Interesting. I see what they did there. We got the same numbers. Okay, these are the same. Okay, these are the same. So GE equals EH. Okay, GE equals EH. So what can we conclude about that third part right there, that part 3? Okay, what can we conclude about that part 3? Whether E is the midpoint of GH? Well, GE equals AH. So by definition of midpoint, okay, that GE, right, GE is equal to EH. Oops, I meant to do a circle here. If and only if E is the midpoint of GH, okay? So our answer here is that, yes, we have established by definition of midpoint that, yes, E is the midpoint of segment GH. And I dropped the mic. I dropped the stylus pen, and hey, we're good to go. So was that shorter than the other video I've already filmed going through this section for you? Probably not. You're probably watching on fast forward and being like, why is this guy so ridiculous? Why is this so long? But hey, you're done now. Go enjoy your Labor Day weekend. That's it. Have a great Labor Day weekend. There is no problem set. I mostly just wanted you to go through this, read the section, ask me questions if you want. You're welcome to start on the problems, on just the problems, and just practice some stuff on your own and email me if you have any questions. But just wait until Tuesday to actually practice this stuff and then use your notes to carry you through. I know this is a weird situation with us just like not being in person with one another, but hey, you're going to be fine. You'll get to ask questions in class, and we'll go over the answers, of course, on Wednesday when we finally get back in class together. Okay. So also, too, another reminder. I know I've said this a couple times, really not as much as I've been hoping to. Make sure you turn in any of your missing assignments from the first 3 weeks. The first 3 weeks of school. So over Labor Day weekend, I'm going to be going through a Google Classroom. Again, I've been slow kind of because I actually want to look at this stuff and get used to you guys. I've been slow to look at all the stuff I've assigned you. So I will be catching up and clearing out assignments and getting your grades in. So you should have a grade next week too. So because of that, as soon as possible, hopefully before Sunday. I don't know if I'll start grading before Sunday. Before Sunday, let's say, make sure all the old assignments, anything you're late on, turn them in, because then I don't have to count them as late for you. Okay, if you do, this is the only time. The first 2 weeks is the only time you can get away with turning in stuff late. If not, I got to start you off at half credit. Okay, so try to get stuff done by Sunday if you're missing. And most of you guys are turning everything. You're fine. You should know if you're missing stuff. Okay, so don't freak out if you're like, I'm not sure if I'm missing stuff or not. You're probably fine. If there's one thing missing, it's fine. Don't worry about it. You're going to be fine. Okay, so make sure you turn in all the stuff in the past 3 weeks as soon as possible. Hopefully by Sunday. And then that'll be good to go. So I can give you full credit here. Okay, Tuesday's homework, asynchronous classwork homework, pages 8 and 9. I'm just kind of giving you a heads up on this. I wasn't planning. I'm not going to often do this. You're going to watch the lecture, take your notes. But hey, if you really want to get started here, you're going to do numbers 1 through 19 odds. And that's on page 8, I believe. Oops, it should have been 9. 9 for 19. 1 through 19 odds, and that's the classroom exercises, page 8. And that should really only take you about 5 minutes. Should really quick, just like, hey, what's the answer to this? Yes or no questions, or true or false. They're pretty darn quick. So that's 10 questions right there, because it's 1 through 19 odds. So that's 10 questions. And you're going to do them, and it's like some of them are like 5-second questions, 15-second questions. So 5 minutes total of work of the classroom exercises. Written exercises, this looks a bit longer, but it's 1 through 39 odds. Oops, 39 odds. And I would say we're planning on working that for about a half hour, okay? So you'll have a couple of problems like this. So picture how much time it took you to do this one. Maybe it took you 5 minutes to do that one. You might have 2 or 3 that are as hard as this, okay? So you might have like 3 problems or so that could take you 15 minutes. And then, so this is 20 problems right here. So 3 problems, expect them to take them a while, but still, a lot of these problems go really, really fast. So about 15 minutes for like 80% of the problems, and then the last few take a decent amount of time, okay? 35 minutes of work, that'll be your Tuesday. If you really want to get a head started on it now, be my guest. Thank you for watching this video, okay? And yes, make sure you do this. Make sure you complete this. Hey, I'm going to circle this here together, okay? Make sure you complete, ugly circle, you complete this homework assignment directly below the notes you just took on this for section 1-2. So when you turn in homework, I check to see your notes are there, and the homework down directly below it, because you do have to take notes in this class as well to make sure you're set up for success. That's it for me. I will talk to you guys later. I'm going to go take a nap. Bye.